Okay.
Good afternoon.
Again. Oh, okay, now it works. Some glitches happen. So, as I mentioned, we will consider inductance. And in order to introduce it, this concept, we'll start from considering so-called self-induction effect. So let us consider some electric circuit. We have a resistor, battery, and here we have some switch S. So this battery will have some electromotive force, plus minus. Now let us consider what will happen when we turn on this switch. So it goes into this position. Obviously that some electric current should flow through the circuit. And the question will be at this time t equals naught, when we turn on the switch, right at that moment or right before that moment, electric current was equal to 0 because the switch was open. And the magnitude of this electric current, as we can easily determine, should be equal epsilon divided by R. So if we assume that there is no internal resistance for this in this battery. So that is the magnitude of electric current which should be set in this electric circuit under given conditions. However, the question will be how, like over time, it will set. So how current will change? Will it change immediately, so instantaneously? Let's say if we have current versus time. So here we had 0 current. That's maybe so 0 current. Then this is our time 0 when we turn on the switch, and instantaneously current increased to this value, which is defined by epsilon divided by R. So indeed, it will not happen like this. And the thing is that every electric circuit when we turn on the switch and current increases, in this area around conductors, there will be some magnetic field created. So this, we know that any conductor with magnetic, with electric current creates a magnetic field. So if current increases, then it creates magnetic field, which also increases in magnitude over time. That automatically means that we will have some time-dependent magnetic field flux through the loop of this electric circuit. So magnetic field flux will also increase as electric current increases. We know that from like Faraday's law that there will be some induced electromotive force equal to negative first derivative of magnetic field flux over time. And this induced electromotive force as well as induced current associated with this induced electromotive force will create, it will be in opposition to the reasons which cause the change of magnetic field flux. So it means that induced magnetic field, induced electric current will create magnetic field in such direction in order to reduce reasons which cause the initial change of magnetic field flux in this circuit. So obviously that there will be some opposition to the process of increasing current I when we switch on the, turn on the switch. So this will cause some delay in the growth of increase of electric current in this circuit, and it will increase not instantaneously, but it will actually take some time to reach this steady state condition when electric current is equal to electromotive force of battery divided by resistance of the electric circuit. If, for instance, we switch, turn off the switch, so we again have open circuit here, then electric current also will not instantaneously drop to zero, because any reduction of this electric current will be associated with change of magnetic field flux. So we will have the same story that induced electromotive force will kind of try to keep the magnetic field flux constant, and that will be in opposition to reducing electric current in this circuit. So taking this into account, we can discuss these effects, what are happening in the scope of such a concept of self-induction. Why self-induction? Because this induced current, which tries to keep magnetic field flux constant, is induced by the change of electric current in the same current loop, in the same circuit. So we don't have some external conductor with electric current where we change electric current, and this causes change in magnetic field in the space around the conductor, some external conductor. And with that changing in time magnetic field, we induce some currents in a different electric circuit. Everything is happening within the same electric circuit. So we change current in electric circuit. This current creates some time-dependent magnetic field, and it's changing. This changing magnetic field creates changing magnetic field flux. In its term, changing magnetic field flux over time induces currents in the same circuit in order to keep the magnetic field flux constant and opposing the initial change of electric current. So that is the self-induction process. So the magnetic field, the induced electromotive force because of such self-induction process, let us denote this as epsilon L, capital L. We can consider it as, according to Faraday's law, as first derivative of magnetic field flux over time. And we can also represent it in terms of the first derivative of electric current which flows through this circuit, because we already understand that the original reason for all these changes of magnetic field over time, of magnetic field flux over time, is because we have a time-dependent electric current in this circuit. So with this, we can write minus capital L times first derivative of electric current over time. This L is a new parameter which we introduced here, and this is inductance of the circuit, of electrical circuit. So from this equation, we can also write that some magnetic field flux will be defined as inductance L times some electric current flowing through the circuit. So this is some proportionality coefficient which relates the provides us the relationship between magnetic field flux through electrical circuit and electric current which flows through this electric circuit. So also what we can write from here that this inductance is equal to EL induced, self-induced electromotive force divided by the first derivative of electric current over time. Also, we need to keep this minus here, di over dt. So if now we compare this expression with equation for electric resistance, we can write resistance is equal to potential difference divided divided by current. Here we see the kind of meaning of electrical resistance is actually the measure of opposition to electric current in the circuit. In analogy to the electric resistance, we can say that this parameter inductance L is a measure of opposition to the change of electric current in the circuit. So the larger inductance, the more difficult is for electric circuit to increase or decrease electric current over time because of this self-induction effect, which opposes any changes of magnetic field flux through the electric circuit. So the units for this inductance are Henry, or can be also represented as volt times second time divided by ampere. So units for inductance are like inductance is measured in Henry units. Henry R. Now we also need to highlight that inductance of electric circuit is a function of geometry, similar to capacitance. Capacitance also determined by geometry of plates of capacitor. And inductance is a parameter which determined by the geometry of the conductors, which are embedded into the electric circuit. So now, if we every conductor is either a straight wire or, let's say, solenoid, possess some inductance, and to be like precise, inductance is kind of distributed parameter because it is present per each unit length of any part of electrical circuit. However, in order to make it more convenient to represent it on electric circuits, similar to resistance, we want to introduce some electrical circuit component, which will already represent all inductance of electric circuit. So for instance, here in this electric circuit, we do not tell that each like centimeter or meter of these wires of electric circuit possesses some resistance. We just represent resistance of electric circuit with just a single circuit element shown here, this rectangular, which stands for resistance. The same element, according to the same principle, we introduce one more element, which is such a coil with some turns of electric wire, something similar to solenoid current wire configuration, and it is marked with capital L, stands for inductor. So electric circuit element, which contains in itself all inductance of electrical circuit, is named inductor and is commonly used in electric circuits in order to show the total inductance of this electric circuit. So now our goal will be to consider an example of such electric circuit with inductor embedded in it. Let us go to another slide and consider such electric circuit. So we will have battery with some electromotive force. And here we will have our inductor with inductance L. Then we will have a resistor R. And we will have two more electrical switchers. So this will be switcher S1, and here will be switcher S2, which has two positions, A and B. So let us assume first that switcher S2 is in position A, so we have larger electrical circuit, which includes the battery with electromotive force epsilon, and at some time less than 0, this switch S1 is open, so we don't have any current flowing in the electric circuit. But at time t equals 0, the switcher, this S1, is turned on, and we want to understand how electric current will change in this circuit over time. So in order to understand what is going to happen here, we need to follow the Kirchhoff's loop rule, transferring the circuit in the, let's consider, clockwise direction. And then we can write that epsilon, the electromotive force of the battery, minus voltage drop over resistor will be current times R, plus we need to subtract also voltage drop over our inductor, and that is proportional to inductance, as we wrote previously, and the first derivative of electric current over time. So that expression should be equal to 0 according to the Kirchhoff's loop rule. You remember that we introduced this Kirchhoff's loop rule for DC, for direct current. And it is necessary to highlight that it's also valid for any time varying current, so not constant over time, or even AC, alternating current, which changes over time and also in direction. So we can apply this rule for DC and AC steady state and transient current electric circuits. So now we can proceed with the solution of this differential equation, because we want to know current as a function of time. And in order to get this function, current as a function of time, we need to solve this differential equation. So first, let us divide this equation for by resistance R in order to make it a bit rearrange, and make it more suitable for us. So it will be electromotive force divided by resistance R minus, actually it will be just current, minus L divided by R, first derivative times first derivative over time. And this is equal to 0. So now let us make a substitution. Let's consider that this is equal to some x. Obviously, dx will be equal to minus di, because electromotive force and resistance, these are just constants. They don't change over time. Now, with this substitution, our differential equation will look as follows. So it will be x instead of minus, we will have plus, because we have this dx is equal to minus di. So it will be plus L over R times dx over dt. this is equal to 0. Now we need to solve this differential equation, which is actually soluble by rearranging variables. So we can have dx over x is equal to minus r divided by L. These guys are constants, they don't change over time. And here we have dt. So now we need to integrate it and get the solution for this equation. So we integrate from x naught to x, and here integrate from 0 to some time t. So we will get natural logarithm of x over x naught, and that will be equal to minus r divided by L times t. X naught, this range from where we start to integrate, is the value of x at time t equals 0. So from here, we will write it on the next slide. If we get rid of logarithm, we can express x as a function of time. Let us write it here. It will be x equal to x naught exponent minus r divided by L times t. So we remember that x, we made this substitution, is equal to epsilon divided by r minus I. And at t equals 0, this x naught, which we use here, will be equal to epsilon divided by r, because at t equals 0, we considered that previously current is equal to 0 also, because we didn't have current in the circuit before we turn on the switch as 1. So now we can substitute back instead of x and x naught their original expressions. So it will be epsilon divided by r minus I should be equal to epsilon divided by r times exponent minus r divided by L times t. So with this, we rearrange this equation in order to get the expression for electric current as a function of time. I as a function of time is equal to epsilon over r. Here we can open parentheses, will be 1 minus exponent minus r divided by L times t. So this is the function which we wanted to derive, and this function describes how electric current will increase from 0 to certain value in the RL circuit. So let's take a look here. If we consider some time, let's say, very large, which approaches infinity, then this exponent term will be negligibly small, will approach to 0, and this current will reach its stationary condition, which is epsilon divided by R. Quite obvious, because this stationary current will be determined only by electromotive force and resistance of the electric circuit. Inductance should not play a role in this case. It plays a role only during the time when we have these transient processes, when electric current is still changing over time. So there is some parameter which can simplify this equation a little bit. So-called tau is equal to ratio L divided by R. And tau is called a time constant of RL circuit. So if we introduce this parameter tau, then the function of electric current versus time can be expressed as epsilon divided by R, 1 minus exponent minus time divided by time constant tau, and we close the parentheses. So the meaning of this time constant, it just defines is a time interval required for the current to increase up to 0. We can put it in percents, up to 63.2% of the maximum value of electric current epsilon electromotive force divided by R. So increase from 0 to 63.2%. And this 63.2% comes from the unity minus Euler's number in minus first power. Because if we substitute instead of T this time constant tau, this is what we get. It's unity minus exponent in the power minus 1. So if now we want to see how electric current, like we want to inspect the change of electric current over time, so we can take a first derivative of this function over time. So let us do it on the next slide. Let's write again this time dependence of electric current in this RL circuit will be epsilon over R unity minus exponent minus T over tau. So first derivative di over dt will be equal to minus epsilon over R times exponent minus time over tau and times minus 1 over tau, because we need also to multiply by the derivative of the argument of this exponent function. So eventually we will get, we will cancel this minus. It will be epsilon over divided by R. And we know that tau is equal to L divided by R. We introduced this on the previous slide. So 1 over tau will be R divided by L. So that's why here we will write R divided by L times exponent minus time over tau. And this will be equal to, so we cancel out this R, epsilon divided by L times exponent minus time over tau. So this is the expression for first derivative of electric current over time. And we see here that the maximum change of electric current will be actually when t is equal to 0. So then this exponent will be equal to unity, and di over dt maximum will be equal to epsilon over L. So if we show this change of electric current over time as a function of time, di over dt maximum, it will be some exponentially decaying function, and maximum will be at t equals 0 and exponentially decaying over time. And this maximum value will be electromotive force divided by inductance of the electric circuit. So one more thing what we need to highlight here, this is actually when we change the position of switch S2. Now imagine that it took some time to establish already steady state electric current, which is equal, I is equal to epsilon divided by R. And then we switch position of this circuit, this switch S2 from A to B. So now A, we don't have anything here. So with this, we kind of eliminate battery from the circuit, and our circuit consists only of inductor and resistor. So now we have some current initially flowing, epsilon divided by R, in this circuit. And since we detached it from electric battery, this current will start to decay with time. So it will start to decrease. So we also would like to understand how this current will decay over time. So in this case, the Kirchhoff's loop law will look like this. It will be I times R plus L times di over dt equals to 0. So we don't have any more electromotive force of our battery because it is eliminated from the circuit. So from here, we can write that I times R is equal to minus L times first derivative of electric current over time. And by rearranging, we can write that it will be minus R over L times dt equal to di over I. So this is our equation, the solution of which will give us electric current as a function of time when electric current will be decreasing, not increasing as we considered in the beginning. So we integrate these two parts and get the following. It will be minus R over L times T should be equal to natural logarithm of electric current plus some constant, because if we don't have defined integrals, we have to deal with some constant. So this constant is determined from boundary conditions. So at time equals 0, we know that at this initial moment of time, we had electric current I equal to electromotive force divided by R. So it was this established steady state electric current in the circuit. So from here, we can write that our constant is equal to natural logarithm of this current in the time equals to 0. So it will be natural logarithm epsilon divided by R. Now, if we substitute this constant, it will be minus R divided by L times T equals to natural logarithm of I minus natural logarithm of epsilon divided by R. Taking into account these features of natural logarithms, we can write that this will be I, like natural logarithm of I divided by epsilon divided by R. And this is equal to minus R over L times T. Now we get rid of natural logarithm, and it will be I divided by epsilon over R. That is equal to exponent minus R over L times T. And from here, we eventually get the expression for electric current as a function of time when this electric current is decaying in the circuit RL circuit. So that is epsilon over R times exponent minus R over L times T, or in other form, it can be I naught, like this maximum value of electric current times exponent minus time over this tau, the time constant of RL circuit, which, as you remember, tau is equal to L divided by R, inductance divided by resistance. If, for instance, L is equal to 0, if we don't have any inductance in our circuit, or it's negligibly small, then this current should go to 0 immediately. So we just switch the change the position of switch number 2, and electric current in this RL circuit with L equal to 0. Then it would be just circuit with a resistor should instantaneously go to zero. However, since we have this inductance there, L, if we look at this plot, where will be current versus time, it will be some exponentially decaying function. Again, it will go from maximum value defined by this stationary condition, electromotive force divided by resistance. And instead of going instantaneously to zero, it will decay over time exponentially. And the duration of this decay will be defined by this RL time constant. So by the ratio between values of inductance and resistance in this electrical circuit. So this is the description of, like, first of all, today we introduced the concept of inductance and consider self-inductance process in electrical circuit. Based on this newly introduced concept of inductance and inductor as an element of electrical circuit, which represents all inductance of the circuit in itself, similar to resistor, which represents all resistance of the circuit in itself. We analyzed so-called RL electrical circuits, to be more precise, transient processes, which give us time dependence of electric current in these circuits in the moment of turning on this circuit, when electric current is increasing over time, and in the moment when we eliminate electromotive force after reaching the stationary steady state condition, when we eliminate electromotive force and let current decay in this RL constant, RL circuit. So all these processes can be characterized by exponential dependence of electric current over time. And one of the important parameters which defines this transient characteristics is tau, so-called RL time constant of the circuit, defined as inductance divided by resistance. Okay, guys, with this, I finished our today's discussion. If you have questions, you're welcome. So next time we will continue with the energy of magnetic field. Similarly to electric field, magnetic field also possesses some energy, so we need to quantify this energy of magnetic field, and probably will consider some electric circuits which contain already all components, electrical circuit components, which we know: resistor, capacitor, and inductor. We'll see how it goes with time, but this is our plan for the future. Okay, thank you very much for your attention, and have a good evening. See you next time. Take care.
Thank you. Bye.
Bye-bye.
Goodbye.